Hello, my name is Peter Flach, and I'm Professor of Artificial Intelligence at the University of Bristol. I will talk about why it is important that AI algorithms stay within their comfort zone when solving a particular task, such as classifying objects, what might go wrong when they venture outside of their comfort zone, and what we might do about it. So let's get started. Would you consider it newsworthy if a human passes a multiple choice test? Probably not. However, multiple choice tests are behind many AI successes that are reported in the media with headlines such as these ones. This all sounds very good, but we need to ask ourselves a few questions here. When we are told that AI passed the test or the algorithm works, what does that exactly mean? And in particular, who sets the exam and what is the passing grade? So let's talk a little bit about performance evaluation. Performance evaluation is not easy. It's not easy to decide how well humans can perform a particular task or how good students are at a particular topic. But importantly, an important aspect of performance evaluation, of being good at a task, is knowing when you don't know something. And I think that is summarized by saying that you want people and machines to be honest about their own abilities. Now, partly this has to do with uncertainty. So weather forecasters are used to quantify the uncertainty in their predictions. They won't say it will rain tomorrow. They will say it will rain with probability 60%, which expresses that it's slightly more likely that it will rain, but they're not very sure. We could actually think about a second level of uncertainty, because we could ask ourselves, is that number 60% the right number? Could it be 50 or 40, or could it be 70 or 80? So just to take an analogy that you probably have heard before, if you toss a coin, if it's a fair coin, you're maximally uncertain what the outcome will be, heads or tails. I mean, you will probably hedge your bets and say 50-50. But you're pretty sure that 50% probability of heads is the right number. It may be 49 or 48, but it's probably not 70 or 30. However, in some situations, you don't know that. You don't know whether the coin is fair. You don't even know whether it's a coin. It may be an irregularly shaped object. So in those situations, it would be much more sensible to say, I don't know. And we need to make sure that our AI algorithms say, I then don't know, when they actually are not sure enough to make a prediction. And this may arise in several situations, which I will talk about. So I will discuss in an accessible way how AI algorithms may sometimes give answers that they shouldn't have. And I will also talk about what we can do about it so that we achieve a situation where AI algorithms are honest about their own abilities and occasionally say, I don't know. I will illustrate the issues with some concrete examples using actual data. And since it's 2021, we will look at some coronavirus data. So here's a map of England with data points plotted on the map, blue and red points. The blue points are areas, locations where COVID numbers are going down, and the red points are locations where case rates are going up. And we want to understand this a bit better. So let's zoom into Bristol. Here's the Bristol area with some data points. We don't have data for all of Bristol because only certain locations report the case numbers, and we want to find out what's going on more generally. So we might want to train a machine learning model to extrapolate from the data and to find blue areas and red areas. And such a model might look like this. Okay, so we have mostly blue areas, means that mostly case rates are going down in Bristol at this particular point in time. And we have some red islands, which are areas where case rates are going up. But actually, what often happens in machine learning is that the model does something like this. So it's the same model, but actually it's now much more keen to make predictions. And in fact, it makes predictions far outside of Bristol. So we see that the whole map, most of the map is colored blue, but there are some red areas. So for example, this machine learning model might predict that case rates are going up in Chepstow on the basis of this particular red point here in Bristol. Or it might predict that cases are going down in Cardiff on the basis of a few blue points in Bristol. So this is clearly undesirable. This is not what should happen. But this is often what happens in practice. And the AI algorithm will not tell you that it's venturing outside of its comfort zone. So let's talk a little bit more about that. These kind of models that I demonstrated here are called discriminative models. They are discriminative because they learn to separate classes. And this could be cats versus dogs, or spam versus ham email, or COVID-19 cases going up or down, as in my example. And they do that by processing a training set and finding characteristics that distinguish the two classes. And by the way, this is called discriminative, which shouldn't be confused with discriminatory, which is when the algorithm is biased against certain groups of people, for example. That happens as well in machine learning, but that's not what my talk is about, and that's not what discriminative means. So discriminative learning is really about focusing on characteristics that distinguish two classes. Okay, that sounds good, and it's great that machine learning can do this. Are there other ways of doing it? Well, there are other models that are called generative models. And they learn not just what separates classes, what separates cats from dogs, but they also learn what typical cats look like and what typical dogs look like. And this allows the model to recognize that a new query, a new question, can you classify this animal? It may be able to recognize that this animal looks very different from anything it's seen before. So why don't we always use generative models? Well, the issue here is that generative models are often much more expensive computationally to train. And because contemporary machine learning models like deep neural networks that you hear a lot about are already very expensive to train, this is almost exclusively done in a discriminative fashion and not in a generative fashion. So to reiterate what might happen in that case, here is another model, in this case a random forest, trained on the Bristol data. And so if you concentrate on Bristol, the areas look very similar, mostly blue areas with some red islands. But if you zoom out, you will see that there are, for example, these red bars going left towards Wales. And so we might classify a particular area of Cardiff as case rates going up purely on the basis that there is this red point on the edge here in Bristol. So I've mentioned the term comfort zone before. The comfort zone is something that it is important to be aware of. For humans, it's often said that you need to venture outside of your comfort zone. You need to learn new things. But sometimes it's also important to stay within your comfort zone and to only do things or predict things that you know about. And that's the same for AI models as well. But the problem is that if you have a discriminative model, it doesn't know whether or not it's in its comfort zone because it doesn't have access to its training data anymore. And it doesn't memorize what typical cats and dogs look like. So it has no way of knowing when it ventures outside of its comfort zone. Luckily, there are techniques for identifying a model's comfort zone. And one such technique called background check works by introducing an additional background class during learning. And I will now talk briefly about how that might work and how that might solve our problem. I will illustrate background check using this one slide that was prepared by my PhD student, Miquel Pereira Nieto, when he presented this work at the conference. So if you look at the figure on the right, and concentrate first on the yellow and blue areas. So there are lots of training data with yellow labels, class 1, and there are training data with blue labels, class 2. So it seems to be quite easy to separate these two classes. And A represents a query point from a typical yellow class, and C represents a point from the blue class. But what about points B and E? Without background check, a model would treat B and E the same. So for B, this is like tossing a coin. You would hedge your bets and you would say, it was right in the middle of the yellow and the blue classes. So I'm going to give probability 0.5 to the yellow class and probability 0.5 to the blue class. And you might do the same thing for point E. But actually, point E is starting to be outside of the model's comfort zone, outside of the area where I've seen lots of training data. So actually, it would make more sense to assign to point E a higher probability of background. The probabilities for C1, class 1, and class 2 would still be the same, but they would become much lower than 0.5. So they could both be 0.1, 0.1. So why is this important? Well, we could now say that we will only make predictions for class 1 and class 2 if the background probability is below a certain value, let's say 0.2 or 0.3. And when the background probability is higher than that, the algorithm should say, I don't know. So this is one way to make the computer say, I don't know, I'm out of my comfort zone. You shouldn't ask me to make a prediction on this data point. And this is in fact a technique that we used to make sure that the COVID predictions were limited to areas around Bristol. So here is an illustration that it also works for random forests. And then we only have predictions from the random forest classifier if the data point in question, the data point that we want to have a prediction about, if that is within the foreground class. And if it's in the background class, the algorithm will say, I don't know. So let's wrap up and look at the bigger picture here. And I have basically 3 lessons for you, which I will summarize. So lesson number 1 is never trust an algorithm that always has an answer. It should be the norm that algorithms will occasionally say, I don't know. Always determine or ask about an algorithm's comfort zone, area of expertise, or operating conditions. So to illustrate the latter, if you have a device such as a mobile phone, the manufacturer will have qualified its operating conditions. For example, it will have said, you can't expect normal behavior in temperatures below minus 40 degrees centigrade, or perhaps above temperatures of 60 degrees centigrade. So this tells you that you should be careful if you take the device to the North Pole or to the Sahara Desert. And the same is true or should be true for AI algorithms. So there should be some kind of label that says, don't use this algorithm in these situations, but the algorithm should be aware of it itself as well and should simply say, I don't know, when it ventures out of its comfort zone. And thirdly, don't expect magic, expect honesty. There's a lot of exciting news about AI and there's a lot of progress being made, but these are still algorithms. There's no magic. It's being made by us and we should think about when it works and when it doesn't work. But let me wrap up with some acknowledgements. So part of this work was funded, supported by the Sphere project. And the Sphere project is about a sensor platform for health applications in a residential environment. Another project was funded by the Turing Institute, which is about measurement theory for data science and AI, so looking more theoretically about what it means to perform a measurement. These issues belong to the area of interactive AI, where we look at interaction between humans and AI. And in Bristol, we train PhD students with funding from UK Research and Innovation. And finally, in Bristol, we are a main partner of a European consortium that looks at trustworthy AI through integrating learning, optimization, and reasoning. And finally, I want to mention my collaborators. I've already mentioned Mikkel. He's been a great help in programming the data examples together with Hao Song and Kasper Sokol. I would like to thank my long-term collaborators and all members of the SAFE AI research group in Bristol. So thank you very much for your attention, and I'd be happy to discuss things further if you want to get in touch.